At this point, we are investigating how to use calculus to determine the shape of a graph. And so, how does the derivative affect how a curve looks? And so, in this video, we'll focus on the first derivative test and what derivatives can tell us about where a graph is, where a function is increasing or decreasing, which will then allow us to start to plot the graph without using a tool like a graphing calculator. So the first thing to think about is that the derivative is positive on an interval um, means that the function is increasing. Okay, so the function either looks like this or like this. And if you think about it, tangent lines along this point will have positive slope, right? So if you have a positive slope on your tangent line, that means that your derivative is positive. And that means that the function must be increasing, right? If the rate of change is positive, think about an application like to population change. If the rate of change is positive, that means that next year there will be more individuals in your population than there are this year. So the number of individuals is increasing. That might look like this, or it might look like this, okay? Or I suppose if the derivative is positive, it could even just be a straight line that's increasing. And so here's an example with x cubed. X cubed has both of these parts, um, increasing like this, where it's kind of facing down. We'll talk about that also very soon. It's called concavity, and it involves the second derivative. And then at 0 here, it kind of evens out, but then it continues increasing, right? Even if it's like facing upwards. So this is an example where the function x cubed is increasing everywhere. It might look a little different on these two intervals, but it's still increasing. On the other hand, if a derivative is negative on an interval, it means the function's decreasing, and the function will either look like this, or again, it's possible the function just has a straight line with a negative slope, so the function is decreasing. Okay, let's see an example where we can apply all of this. So in this function, we don't know what function this is. We just have the graph of it, but there's a lot going on here. We have places where there are cusps. We have some local mins, and places where it sort of evens out, some maxes. And we can see that these are all the critical values, right? A, B, C, D. Those are our critical points or critical values. That's where the derivative is either 0, right? In these three cases, the derivative is 0. In A, it's where the derivative doesn't exist. The derivative is undefined, right? It's not differentiable at this point. It has this sort of cusp. And so those are all of our places where local maxes or mins can occur. That's what we've seen. Let's look at the derivatives in between these points. So before A, the derivative f prime is positive, and we can see it's increasing on that interval. And then afterwards, the derivative is negative, and it's decreasing. And so we go from increasing to decreasing, which means here we must have some sort of maximum value. Okay. The only time that that wouldn't be true is if we had an asymptote, right? We can imagine that happening if we had a vertical asymptote. It might be increasing here and then doesn't exist and then decreasing, and you wouldn't have that would be a case where a global maximum wouldn't exist on the graph. Okay, and then the derivative is negative, it's decreasing. We get to this point where the derivative is 0, and then the derivative is positive. So if the function's decreasing and then it's increasing, that means this must be a local min. If it's increasing and then increasing again, increasing, levels out, increasing again, it means that this point it might be a critical point, but it's not a local max or a local min. And then at the end here, point D, we have that the function's increasing, the derivative is positive, and then the derivative switches to being negative. So it's increasing and then it's decreasing, and that makes this point D a local max, which also looks like it's a global max too. Okay, what about if we're just given an equation for the function? and not a picture of it. So what we can do is we can take our first derivative. In this case, that will be 3x squared plus 9x minus 12. And go ahead and find our critical values. So we'll think about setting this equal to 0 and solving for x. What we get is we get 3 times x plus 4, x minus 1. So we get two critical points. X is -4 and x is 1. Now what we want is we want to do something similar to what happened in this picture. We want to figure out on each of these intervals what's going on with the derivative. So we'll do something called a sign chart where we say, okay, our critical points split up the whole number line. And what we want to know is what is happening with f prime on each interval. So what we can do is we can plug in different values into our derivative to see if the derivative is positive or negative on each interval. So for example, here, what we might try is we might try f prime of -5. And what we'll get is we'll get 3 times -1 times -6. And we can see that the derivative is going to be positive on this whole interval. If we plug in 0 for the middle one, because 0 is between -4 and 1, then we'll get 3 times 4 times -1, which is going to be negative. So the derivative is negative on this whole interval. And then after 1, let's say we plug in the value 2. We could plug in anything that's larger than 1. Let's just plug in 2. 3 times 6 times 1, that's positive. So what we get here is we know that the function is increasing and then it starts decreasing. Okay, so it's increasing and then decreasing at the point when x equals -4, which makes that a local max. To determine if it's a global max, you'd still have to plug it into the original function and sort of figure out what the value is. Now here we have that the derivative is negative and then positive, so it looks like this. And at this value, this is the value 1. It's decreasing and then increasing. So that means we have a local min here. So using our sign chart, we can see where the function is increasing or decreasing, where it has its local maxes and its local mins.